So hi, I'm Rahul, and today we will be talking about Beaver, practical partial snapshots for distributed cloud services. Before we go a little deeper into Beaver, we should talk about distributed snapshots. Distributed snapshots are a mechanism that allows for generating a globally consistent view of a system. So one way to think about this is to imagine that we have a beautiful blue sky and we want to get a picture of the whole sky with some birds in it. They are going in some direction. Unfortunately, the camera we have cannot take a picture of the very big sky. It has to take small parts of it. So we can then assume that capturing small pictures of the different parts of the big sky and stitching them together can provide a consistent view of the sky, right? But if we think about this solution a little deeper, we realize that if we are not careful in taking the pictures and stitching them together, we can get a view of a sky where the total number of birds are more than the actual number of words. And the reason can be by the time you start taking picture of a different part of the sky, the same birds that were in your previous frames might have just flown into your current frame. Hence, the picture that you get is not a globally consistent view of the sky. So we want a snapshot that is consistent. And this snapshot provides help in deadlock detection, checkpointing, debugging in distributed systems scenario. Mathematically, it has been defined and it means that if C is a set of events that every process C is a set of events on every process before the cut, then C is causally consistent for each event in C if we always have an event that caused that particular event. So if E prime always causes E and E is in the consistent set, then we always have to include E prime in our set. And if we have a transitive closure on this relation, that means our whole snapshot is consistent. So if we think about it, imagine that we have two processes, P0 and P1, and then there are some relationship between events. For example, E3 leads to E0, E1 leads to E4, and E5 leads to E2. So if we were to cut this process graph given by the two dots, one is a solid colored gray dot and one is a shallow colored dot, that means we have included all the events including the events that caused it. So for example, our consistent cut makes sure that we get events E3 and E0 in it. And E0 is caused by E3. That means our snapshot is consistent. If we were to have this cut, the bottom right dot, which is the shallow one after E4 and not including E1, that means our snapshot will be inconsistent because E4 is caused by E1, but we did not include it. So another way to look at this example is, which is a much simpler example, is imagine that you have two bank accounts. Account one has $10 in it and account two has $100 in it. And we want to have a transaction which moves $5 from account one to account two. Imagine these two accounts live on separate machines too. We have to employ some kind of a 2PC mechanism. And the end state is that account one will end up $5 because we subtracted 5 from it, and account 2 will have 105, 5 moved. So if a global consistent cut will always mean that we have a snapshot of account 1 and account 2, either in the previous state, which is 10 and 100, or 5 or 105. But if we are employing 2PC and stuff like that, there might be cases where you end up reading 10 and 105 because we released the logs on some machine earlier before the other one. But 10 and 105 does not give you the consistent view of your bank account because essentially you do not have 105 plus 10, which is 115. Instead, you still have the old money, right? So we need to have a consistent snapshot which tracks all the events and the events that caused it. And if we account for that, we end up either in the start state or in the end state. So the traditional algorithms, there have been many algorithms that have been suggested to implement such a thing. One has been Chandi-Lamport algorithms and many others. All these algorithms assume that the participants are closed under causal propagation. which means that you're able to modify or you're able to run your software or whatnot on all the machines which are participating in your distributed snapshot, which is not true for modern cloud deployments. For example, you can have a service that can talk to multiple services which are not in your cloud. For example, you might be running your service and that service might be talking to SNS. That service might also be talking to SQS or a Hugging Face interface for ML services. These services, which are external to your services, are total black boxes and cannot be observed. So you cannot deploy some random software that allows you to capture the snapshot. So these traditional algorithms cannot work in such situations because we do not have a way to control or send messages or receive messages from these external services. So one such example is, imagine that you have P0 and P1, two processes, right? Which in-group processes. I'll go deeper into what in-group processes means. But imagine these are the two services that you control, and then there is some out-group process that you don't control. So you cannot have your software installed, which can help us participate in the distributed snapshot. So if we were to get a consistent cut in this scenario, we can also get E5, E prime 5, and E3, which might be fine from a traditional point of view, which makes sure that all the participating entities are there. But in this case, we forgot E4 prime because there is no way or there is no causal change from E4 5 to E prime 4 to E prime 5, right? It is only through the external entity. E4 prime, E prime 4 goes to out of group process, comes back as E prime 5, right? So if we were to include E prime 5, we have to include E prime 4. But our traditional algorithms cannot help solve these scenarios because there is no direct causal relationship between these two events. So this is where Beaver comes into play, and Beaver suggests that instead of getting a traditional snapshot, we can get partial snapshots. In partial snapshots, processes are divided into two groups. One group is called in-group processes. The other is called the out-of-group processes. In-group processes are the processes that are of your interest that you want to take a you want to take a snapshot of. And out-of-group are the processes that you don't want to, or either they are out of your system and you cannot, right? So mathematically, a partial snapshot is defined by the following definition. If P is the set of all in processes and out processes, and the intersection is null, so we are trying to say there is no other process. And C part will be a pre-snapshot event for P in. Remember, this definition only takes care of the events for P in. We are not concerned about the messages initiated from outside. And C part is causally consistent. We go through the same definition again. That is, E prime belongs to P in. That means the message should be from the in process, and it should be closed under the causal relationship that if E is part of the consistent set, then the E prime which caused it should also be the part of the snapshot. Beaver utilizes this concept and provides the following three features that makes it suitable for today's deployment models. Only deploy in your in-group machines or the machines of interests so that you don't have to worry about the external machines not cooperating. It promises zero or minimal cost for data center infrastructure and near zero impact on existing data center service traffic. That means your existing machines don't have to do heavy computation that can hamper your application traffic, and it provides a minimum cost solution to this problem. To solve the problem of interfacing with external entities that are total black boxes, Beaver introduces a concept of a gateway marking. Imagine a system sitting between your in-group process and out-group processes or external services. The idea is that we route all the packets from your out-group machine to your in-group machines through the gateway. So you have your in-group processes and you have your out-group processes. And then there is this machine or whatever system that sits in between. And it routes all the packets from out-group to in-group, right? Remember, or if you think more, we are not concerned about messages which go from inside to outside. We are only concerned with messages which are coming from outside. And we'll see how this ties into the correctness of the problem. And the responsibility of this gateway is to tag all incoming packets to our incoming groups with the snapshot markers, right? And this gateway marker is also responsible for initiating the snapshots. So for example, using gateway marking, we can get a snapshot which does not include E prime 5. As we saw in the previous example, a couple of slides back, where E prime 5 could be included, which was causally inconsistent given the fact E prime 4 was not included. But if we use this algorithm, we end up excluding E5. I'll show later how we can exclude it, but the idea of gateway marking is to tag the packets in such a manner that the snapshot we get is able to identify which event is part of the snapshot and which is not. But the gateway that we just talked about is a single machine. And in today's deployment, the number of services or the external black boxes you talk to can be huge. So this assumption that we have only one gateway marker machine is not correct. If we are not careful with our algorithm, what can happen is this gateway marker machine that we have two, they might not see the snapshot start at the same time, and it can also give us a wrong snapshot again, right? So just imagine the case that we have two snapshot markers, G0 and G1, and the solid dot on the first one, G0, shows where the snapshot began. But the fun thing is G0, the gateway marker, knows the snapshot has begun. Therefore, all the messages which are flowing through it will be tagged appropriately. But if a message goes from in process to out process, but comes via G1, and G1 has not started the snapshot process, that means the message will not be tagged and might be included on our consistent snapshot. So this is a very good example which shows that a message goes from inside, which is E4, E prime 4, goes outside, comes back inside, even though we have started the snapshot process, which is evident on the G0, but G1 has not received the message to start the snapshot process. Hence, the message that comes from G1, which is E9, E prime 9, and reaches as E prime 5 on P1 machine, is not tagged and therefore can be included in the snapshot. But this is a wrong snapshot because E prime 4 has to be included, or if it's not included, then E prime 5 has to be excluded. But G1 does not have a way. So having a single machine helped us because that single machine provides a consistent point after which all the messages will be tagged. But having multiple gateway marking machines, this becomes a problem. To solve this, we have to think about what kind of messages are we concerned about. So the key idea is that only a subset of incoming traffic to our in-group is causally relevant. So if you think about it, the message which goes from gateway A to INA means our in-process machines, then goes out, but comes back in via gateway B. This is the time window during which if snapshot information is being propagated, and if a message comes in between this one, that means our snapshot will not be causally consistent. So again, to go in this one, snapshot marking has begun on one of the gateway markers, and it has not completed on all the gateway markers. Meanwhile, there is a message that goes from inside to outside and comes back. It sees a gateway with snapshot on, and then it sees a gateway with a snapshot not on. And this happens because the time duration during which the snapshot has to propagate to all the gateway machine can take some time. So if this thing happens, then our snapshot is not consistent. So mathematically, they are trying to say the same thing. So if you look at it, let the wall clock time the first and the last snapshot gateway initiating snapshots be ESS, G min T, and min ES. So ESS means the snapshot time event or and for the gateway. So it says the min time and the max time should be less than T min. What is T min? We'll get back later, but essentially it is trying to say that if you have a start time when the snapshot started on the gateway and there is a end time when the snapshot ended, because all the machines know, all the gateway markers or the gateway machines know that the snapshot has started, and it has to be less than T min, then the snapshot will be causally consistent. So one way to think about it is if G0 and G1 are gateway machines, and these solid dots mean that the snapshot process has started taking place. So we can approximate by saying that if T0 time, there's an OOB controller, which means out of band controller. So here we start the snapshot process, goes to G0, goes to G1, and then we receive it back at T1, right? And we can assume that if none of the messages pass between T0 and T1, then we are fine, right? Okay, so I have evaluation after that. Okay, but the whole point of this algorithm or the theorem that we were discussing before is that if we were able to bind this time by saying that if T0 minus or T1 minus T0 is small enough that none of the messages pass, that it means that the snapshot is causally consistent. There are 4 questions that this paper asks. Can Beaver sustain fast snapshot rates? How often do Beaver invalidate snapshots in cloud data centers? Now, why are we talking about invalidation is if there is a message which goes in this window, we should be able to detect that, and we should be able to discard that snapshot. How does Beaver's distributed coordination affect existing service traffic? So running this Beaver's software, how does it impact your existing services? And how does actually, the last question is, how does Beaver actually help in your real world scenarios? So the first evaluation graph that I saw from there is that Beaver sustains snapshot frequency versus like different number of gateway markers. So on the left graph, you can see that the frequency we have, and on the bottom, we have the number of gateway markers. So as the number of gateway markers increase, the snapshot frequency decreases. So the first graph is without parallelism, and the second graph is with parallelism. This again is the effective rate of snapshots. So effective rate means you can have large number of snapshots taking place, but some of the snapshots will be invalid because the constraint that we talked about, which is your start of snapshot time, end of snapshot time, should be less than the T time, which is the message loop time. And that can render a snapshot correct or an incorrect. And essentially, we are trying to say that these small blocks you see 2, 4, 8, 16, the number of gateways and frequency, and what is the snapshot effective rate, like which one, how many of them are correct. So this graph was kind of all of them reaching 90 plus, right? So even for 1024 frequency, 2048 frequency, and 131072 frequency, Beaver is able to take very large number of snapshots really fast. This is a graph which shows the load on a particular machine when the Beaver is running. There is very minimal impact on the application workload. And one of the use cases that they talk about 7 use cases, but one of the use cases that can help us solve is, imagine that you have 2 services in your cluster. One is a search backend, one is a stock backend. So your usual flow of users using the application is using the browser front end, they search for something, they get the result, and based on the result, they make a query to stock backend and get a result, right? So if we use traditional consistent snapshot algorithms, we will not be able to see this external causality of like first they search and then they make a call to a stock backend, right? Because we do not have control on control on browser front end. And as a result, Beaver can help us in determining these situations where we can validate that, okay, first a user searches and then call goes to stock backend, and all the other calls which are currently coming from browser directly to the stock backend can be a bot access, because usually our users do the other way around. So Beaver can help you detect such patterns and situations where external causality can be measured and calculated, and then you can take some actions by dropping this traffic or moving them to lower tier and whatnot. That's it. Thank you.